Okay, first to introduce myself, my name is Ivan Kelly. I work for a company called Streamlio, and we're building a stream processing platform on top of Apache Pulsar, which is what this talk is about. And specifically, I'm going to talk about infinite topic backlogs for stream processing. So I'll lead off with a quote by Peter Norvig. He's a big AI guy in Google. We don't have better algorithms than anyone else, we just have a lot more data. And I'm sure they do have some very good algorithms, but the point he's trying to make is that when you have a lot of data, you will be forgiven for making bad choices in your algorithms, bad choices in your parameters. And this is especially true in cases where a rare event will have a disproportionate impact on the final product. A good example of this is web indexing or web crawling. If you come across a link while you're crawling for the first time, that occurrence of that link is going to have a larger impact on your final index than if you had come across that link 1,000 times before. And data with this kind of Zipfian pattern is very common in the real world. So if you have a lot of data, you can predict around this data very well. So I'm going to use an example system, an example streaming system, just as a basis for the talk, and just to give a bit of background of what these systems look like. Usually, you have in a recommender system, you have user inputs. This generates user events, which then gets fed into a stream processing engine. I'm only going to talk about streaming. I'm not going to talk about batch at all. The streaming engine then processes the user inputs to produce a model, which is then used to serve more results of some sort to the user. To give a concrete example, let's take, say, Spotify. Spotify watches what songs you're listening to, and then it takes these songs, feeds them into an algorithm, which then generates a listening model, which then recommends the next song you might like to listen to. Like you get these your daily mix, or also you have the weekly one as well. I can't remember the name of it. It's important to note that you have to take into account historical data and live data. If a user has been listening to the same music for 20 years, you want to make recommendations to them based on that 20 years of listening. But also if they've discovered a new band recently, you want to take that into account when giving them new music. Maybe you want the new band as a new album that you want to send them. So you have to use all the data. And you can't just process this data once and throw it away. You have a whole team of data scientists and data engineers working on the newest and greatest algorithms, and they need to validate their work. And once their work is validated, they need to be able to push that into production. And once it goes into production, you need to be able to run the whole backlog of user data against that so that the users will get the best experience. So this kind of architecture, where everything is a stream, is generally called a kappa architecture. Well, what people often end up with in the end is something like this, which is called a lambda architecture. So live events are processed in a pretty similar way, but you end up with a partial model, and then historical events are stored somewhere else in, let's say, a HDFS, HBase, or if you're using cloud, Bigtable, S3. And these are processed in a different processing stream, and then the models are combined to provide the results to the user. And this works, but it's not ideal. You have two sets of systems that you need to maintain. You need to hire people who know how to work with them, know how to debug them. You also need your developers to develop their code twice. They need to do it in a batch system, and they need to do it in a streaming system. And the reason you have this lambda architecture is because, well, a lot of times the live user inputs, the messaging system these are coming in on isn't able to support huge amounts of data. For example, Kafka is often used in this use case, And Kafka is limited by the amount of local storage you can fit on a single node. For a single topic, that topic is limited by the amount of data you can keep on a single node. Ideally, what you'd like would be to have just a streaming system and store all your data in the live user events. And that's what this talk is about. So Apache Pulsar allows you to do this. It pretty much can fit all of the boxes in this diagram, but I'm only going to talk about the topic backlog in this talk. So a brief introduction to Apache Pulsar. It's a messaging system. It offers pub sub and queuing semantics. It started in Yahoo maybe 4 years ago. Yahoo have this massive distributed database called Sherpa. And Sherpa's been around maybe 15 years now, I'd say. They need a system for a write-ahead log for Sherpa. So anytime you write anything to the Sherpa table, that needs to get first written to a persisted replicated log so that if the table crashes, stuff can be replayed. Standard write-ahead logging stuff. Historically, they used NFS filers for this, and it was a massive pain, and they were trying to get off this for years. I joined Yahoo in 2010, and by the time I left in 2015, they were still trying to get off it. And there was a number of attempts to get off it. There was one called Hedwig, which died for political reasons. There was one based on ActiveMQ, but they found that the brokers in ActiveMQ couldn't scale. Some people suggested using Kafka, but Kafka wasn't able to take the number of distinct streams, because this database had like hundreds of thousands of different tables, and each table has its own topic. So you can imagine the number of Kafka nodes you'd have to do, and that's because how Kafka stores stuff on disk. So eventually they decided we're just going to write our own messaging broker, and that's where Pulsar came in. And because it was targeted at this use case, we got a lot of nice features built in from the get-go. Stuff like multi-tenancy, geo-replication, strong persistence. But I'm not going to really talk about that stuff today. I'm going to talk about unlimited topic backlog size, tiered storage, briefly go into lightweight compute in a demo, and I'll cover the SQL interface for the infinite backlogs at the end. So what do we mean by a topic backlog? When a client wants to publish a message to the messaging system, they'll generally publish it to a broker. Then the broker will persist it to a replicated log somewhere. You need the step where you write it to the replicated log for the case where the broker will fail. You want, well, actually, not even that when the brokers fail. You want all consumers to be able to get all messages in the same order without getting duplicates and this kind of thing. So having a replicated log for the topic backlog makes this possible. So an important thing to note is that Pulsar will only acknowledge a write of a message once that write has hit the replicated log. And the replicated log will only acknowledge a write to the replicated log when it can guarantee that that has hit physical storage on each of the disks, on each of the replicas. So this is, it uses fsync, in other words. Go. There we go. So each backlog in Pulsar is broken up into segments, and you can have two types of segments. You have open segments and closed. So I went too fast this time. Open segments and closed segments. So an open segment is the current segment in the topic backlog that's being written to, and the closed segment is basically every segment previous to that. Once a segment has been closed, a segment becomes immutable. What this means is individual messages cannot be deleted or modified or anything. It's immutable. If you do want to delete stuff, you have to delete a segment at a time. And this immutability of closed segments is very important for tiered storage, as we'll see later. I think that's all I have on that slide. Oh, another important thing to note about segments is they are entirely independent of each other. So the broker knows the order of the segments with regard to each other, but the segments don't know anything about each other. So a single segment, like this segment, may be replicated to storage node 1, 2, and 3. The next segment in the same topic may be replicated to storage nodes 4, 5, and 6. And because of this independence, it means this is how we can scale the topic backlog infinitely. Like if you want to keep adding segments, you just keep adding storage nodes. I'm going to how that happens now. So an important architectural decision in Pulsar was to keep the serving and the storage layer separate. So let's say you didn't do this and you put storage and the serving layer, like the broker, put the actual storage on the brokers themselves. In that case, if you wanted to scale a single topic, that topic would be only assigned to one set of brokers, and that's why you would have a limit on the size of the backlog. You wouldn't be able to have part of a topic on one broker and part of a topic on another broker. So this separation gives us really nice scalability properties. And like in Yahoo, I think they only have one single cluster of Pulsar. And last I heard it was 1,700 nodes. So it's a big cluster. Twitter are actually also using the storage layer, because the storage layer I'm talking about is a bookkeeper, and I think their deployment, they have a single deployment as well, and that's in the magnitude of 1,000 nodes. The storage layer of Pulsar, which is Apache Bookkeeper, scales very, very well. But also, separating like this allows you to scale for different use cases in different ways. So if you have a use case where you have a lot of reads on your topics, your bottleneck there is going to be network bandwidth. So to increase the amount of network bandwidth available to your system, you can increase the number of brokers while keeping the storage nodes fewer. And this is important because storage nodes tend to be more expensive than the broker nodes. The broker nodes only need CPU, network, and memory. The storage nodes need all that, plus a whole load of SSDs. Well, it doesn't have to be SSDs, but a whole load of disks. Disks are expensive. Conversely, if you have a use case where you have a write bottleneck, so you have a lot of topics that are being written to, then but like modest number of reads, then you would scale your storage layer. And you do this just by adding nodes, and the system picks them up automatically. But it doesn't, so actually I'll show you how this works now. So let's say you have a topic backlog. You're adding segments. And eventually your storage nodes get a bit full, and like, I should do something about this. So you just add another storage node. The system won't rush and start to push all new data to the new storage nodes. When a new segment occurs, or when a segment rolls, it'll just move one replica of that segment to a new node, and it just avoids the herding that can happen. It's also important to note that sorry, my voice is gone. It's also important to note that there's no rebalancing here. So this was one of the requirements when they were evaluating Kafka for this Sherpa write-ahead log layer. These tablets need to be up forever. Like, they cannot go down. If, to expand your storage, you need to do a rebalance, which is what you have to do in Kafka, then the storage nodes would have to go down. So Pulsar avoids this by using this bookkeeper storage layer. But this can get expensive. If you're storing massive backlogs, that's a lot of data that you have to store for a long time, and eventually your finance people are going to knock down your door. And this is because it's doing 2x replication. Well, in the previous example, it was 2x replication. And this is actually pretty inefficient. So when you do 2x replication, have this, well, in this case, it's 1 over n efficiency, which is basically half. You're getting half as much storage for your money than if you weren't taking fault tolerance into account. Of course, you have to take fault tolerance into account, but there are better ways to do this. And this actually just gets worse as you start adding replicas as well. And the better way to do this is to stripe across disks. You put one block on one node, another block on another node, another block on another node, and then you combine all these nodes to blocks to generate a parity block that you then put on a final node. When one of these nodes then fails, you can regenerate any of the failed nodes by taking all the blocks together. The most common implementation people would know of would be RAID. But Colossus, like Google's successor to GFS, certainly uses the same stuff as well. It's one of the main differences with GFS. So this striping with parity, it has a space efficiency of 1 minus 1 over n, so in this case, we have 6 nodes. So the space efficiency is 0.8. You're getting pretty close to 1, which is obviously the maximum space efficiency. In this case, it's to tolerate 1 failure, but you can do something, just add another parity block to tolerate 2 failures. You only really need to tolerate 1 failure in Pulsar. Well, I'll go into that later. But Pulsar, when a node fails, there's a background process that goes and sees which segments are on that node, and it uses the other replica to bring the number of replicas back up to the what is specified in the segment metadata. So this kind of system is very nice. And if you could store your infinite backlog in this kind of system, you would save a lot of money. However, you can't store all of your backlog like this. So for closed segments are immutable. They can be copied anywhere you want, and then you can just add a pointer to them. That's no problem. The open segment, you're writing to that segment. And if you had to wait for enough blocks to be complete so that you could generate a parity block, then your write latency would just go through the roof. So we can do it for closed segments, we can't do it for open segments. And actually, we don't actually implement this kind of striping ourselves at all. We use some other storage system. And it can be any other storage system. What I'm talking about is the mechanism to put stuff onto long-term storage. So for example, S3. It works like this. So you start writing stuff to your broker, new messages, segments start getting created, and eventually you hit a threshold. There's 2 types of threshold for tiered storage. Time-based threshold, like anything older than a day, move it over to long-term storage, or a size-based threshold, like when the topic backlog reaches 10 gigabytes, move it over to long-term storage. So when you hit the threshold, you just start copying segments to long-term storage, and you can delete the segments from, well, you don't have, the segments are marked to be deleted on the, I don't want to say local storage because it's a distributed system, so it's not actually local, but the storage that is part of Pulsar gets freed up. And this means you can actually have quite a small pool of storage nodes, which, as these are the more expensive nodes, will save you a lot of money. The client, when it's reading back this data, it doesn't need to know whether it's in long-term storage or in the Pulsar storage. The client interface is still the same, and it's the broker that actually does this for you. This is another advantage of separating the serving and the storage layer. So the process for offloading is this. You can read it, but I'll explain it too. When the system decides that it wants to offload a segment, the metadata for that segment is updated to say we're going to offload this, and it leaves a hint where it's going to offload it to. We do this to avoid the situation where we crash partway through an offload, and then you have this chunk of data just sitting around in long-term storage forever. So like that happens enough time, you just start leaking storage, and that storage you need to pay for too. So we write this hint in the metadata, and then we start copying the entries in that segment byte by byte. We also keep track of an index of the offsets of the messages within that segment, so that when we come to read back, we won't have to read the whole object. You can just jump halfway through and read forward from there if you need to. Finally, when everything's been copied, we update the metadata to say that this segment has been offloaded, and then we have another background process which will delete that segment after a grace period. We don't delete it straight away, just in case something goes wrong and you need to pull the plug on it. So we give it a grace period. Right now, we have a couple of different backends for long-term storage. We have S3. This is the oldest one. This was implemented last summer. Google Cloud Storage came a couple of months after. We also have an implementation for Microsoft Azure and Hadoop, HDFS, but these haven't been merged yet. The pull request has been open for months, but priorities and stuff falls off the radar. But we're going to get it merged soon enough. Okay, so I've gone through how the segment-oriented architecture of Pulsar allows you to grow your topic backlog infinitely. I've gone through tiered storage, which allows you to store this infinite backlog relatively cheaply. So now I'm going to give you a demo of how this works. So I have a Pulsar cluster set up. I have one topic. There's a connector for Twitter Firehose. It's been running for about 2 weeks now. And that's writing data into one topic. This topic it's getting quite large now. A lot of the data is being offloaded to S3 automatically. I think I set the threshold to like 10 megabytes or something, so it would automatically offload very quickly. And then this data is being fed into a Bloom filter function. This Bloom filter function is running on the lightweight compute engine that sits on top of Pulsar. It's a very, very simple function. It's a toy example. And this can also take a query and give you a result whether a word has appeared in the Twitter stream. Okay. So this is that's the query. The query is actually very simple. You give it, wait, I'll make this bigger. Why is it not? Oh, my SSH session has died. 1 second. Oh, demo. Okay. It's a nice responsive network we have here. Okay, so we set up the client is very simple. You set up a Pulsar client, you subscribe to the result topic, you create a producer on the query topic, and you generate a unique ID for the query request. Then you send the query to the to the query topic, and then you wait for a message to come back with that request ID in its payload. Then the actual function is it's super simple. So this function, it takes in a string, loads the string, it checks if it's a query or if it's a text. So if it's a text, it means it's coming from the Twitter stream. If it's a query, it'll run the query against the Bloom filter, which we've set up here. The query in the Bloom filter is just using the in operator in Python. If it's a text coming from a tweet, you split it add each token to the Bloom filter, and you also keep track of how many tweets you've processed. So, why? Oh my God. Okay, I've lost all my sessions, so I'm going to have to remember this from the top of my head. It was in Pulsar. I actually gave this at Strata 2 weeks ago. That's why it's named as such. So CD client. So we'll run a query against it now. Has it killed my session again? The Wi-Fi. Let me just try one more thing, and if that doesn't work, I think I'll just have to abandon this demo because come on. Okay, no. I've tried it on my own phone, so I think there's a lot of Wi-Fi interference here or something. Let me try one more time. That's one more option. I can try over Bluetooth. No, okay. I'm going to have to abandon this demo. But if you want to see the demo, just come up to me when I'm not on stage and the Wi-Fi is working, and I can show you all this working. So what I was going to show was doing a query, showing you the infinite backlog, like querying the stats of the backlog, showing you how much data is in each. There's about 20 gigs of data in the Twitter topic. A lot of it is trash, actually, because like to give you this fire hose, and almost every second message is a delete. I don't know, a lot of people deleting tweets these days. And then join the Bloom filter is overmatching. I would increase the number of entries in the Bloom filter and then run it again and run the whole backlog against it. But the demo gods are not willing today. Okay, so finally, querying massive backlogs. So it's all fine if you have like all this data, but sometimes you want to give access to this data to analysts or people who don't want to write code. And for this, we have Pulsar SQL. So Pulsar SQL, it provides an SQL interface over Pulsar data, and it's based on PrestoDB, which is a database backend provided by, developed by Facebook, but it has pluggable backends for many different storage layers. So something I didn't mention earlier is that there is each topic in Pulsar can have a schema, and a schema like this, it says what kind of data it can accept. There's also ways to evolve the schema, check that schema is valid, etc., etc. So this topic schema is used to generate the table schema. And the table schema is then used for, well, that's what you use when you make your queries. An important thing to note is that Pulsar SQL is for data at rest. It's for data that's already in your storage system. It's not for data, it's not like some streaming systems where you write a query and then you get all the new results as the data comes in. So we deploy it like this. So Presto has a coordinator, and then you have worker nodes. When you do a query, the query goes to the coordinator, then that gets split into blocks, and then that gets farmed out to the different workers in your cluster. The workers actually go directly to storage. They don't go to the broker. Because when you do a query on a large backlog, you have to read all the data. There's no indexing in Presto. So since you have to read all the data, if you went through the broker, you would end up just trashing all the caches in the broker, probably overloading the CPU, and impacting the performance of production data, production traffic that's coming into the broker. So Presto knows how to go to the storage directly. It knows how to go to the Bookkeeper, the Pulsar storage on Bookkeeper, but also knows it also can use the plugins for going to long-term storage. And now there's supposed to be another demo. Let me just see if situations have improved. No, okay. So again, I can show you the demo if, well, if you come up to me and we can go through this stuff. Unfortunately, couldn't do it live. So to summarize, Apache Pulsar, it allows you to have unlimited backlog size. The older data in that backlog can be moved to long-term storage to reduce the, yeah, I'm fine. I have about 10 minutes of demo that I haven't done. The older data can be moved to a long-term storage to reduce your costs, and then all this data can be queried with an SQL interface. Now, the motivating example I used at the start was a recommender system, but there's many use cases where just having a long, massive stream of data is very useful, such as queues, event sourcing. I'm not going to say the whole acronym. And that's it. Finishing a little bit early, but again, if you want to see the demos, come talk to me. If you have any questions, happy to ask them, or you can get me on Twitter. Happy to answer questions there as well. Thank you. Cool.
Thank you very much, Ivan. Very interesting. I'm going to check if there are questions. I did a few minutes ago, and we had no questions.
Yeah.
So sorry, I apologize. I forgot to mention that, well, I do it after every chat, that at the beginning of the chats, that you have a place, you have a URL to make questions. So if you haven't had the chance, you can raise your hand, and we can pass the microphone, you know. All technology also works. So, any questions over there? Okay.
Yeah.
Hi. I really like how much deep on the implementation you enter, like explaining how this core and all these kind of things. There is more documentation about that on the
Well, so yes, the blog, any feature we've implemented, at Streamlio, we've put a blog at Streamlio, but there's also documentation on the Pulsar website as well. Some of it, like with all open source projects, it can be improved, but there's enough there to get you started. We also have a Slack channel. If you have any questions, just pop into the Slack channel, and there's usually people around who can help you, especially during when like West Coast US are awake, because that's where the majority of the people are.
Okay, thank you very much.
Yeah.
So, hi, thanks for the presentation. My question is this tool a good replacement for Hadoop ecosystem? Like you can replace Hadoop, HDFS, Kafka just by using this tool?
Sorry, say this again. Can you replace all of these things just by using Pulsar?
Yeah, if you can replace an existing Hadoop cluster, like HDFS.
Well, it depends on your use case. But if all your data is streaming data, then yes.
Okay, thanks.
Any other questions?
One more question. If the nature of the messages are snapshots of each message, like imagine like prices, does it support some type of compactation of messages?
Yeah, we have compaction built in as well.
Okay, cool, thanks.
Well, I think this is enough. Are we done? Yeah. Thank you very much, Ivan.
All right.